So, we are now going to look at the next topic, namely computing the inverse Z transform. So, as mentioned before, we will confine ourselves to the class of rational transfer functions. So, we will assume that x of z is of the form p of z over q of z. So, which means that this is rational, and in particular we will assume that this is of the form 1 plus q1 z inverse q2 z to the minus 2 up to qn z to the minus n, and the numerator we will assume to be of this form Pm z to the minus m, ratio of polynomials. Now, just a couple of observations about this. Here we have assumed that this leading coefficient of the denominator is 1. This is not a restriction, because if the leading coefficient were not 1, we can always normalize it so that the leading coefficient becomes 1. So, this is perfectly fine, it is not restrictive. The numerator is assumed to be of the form P naught plus P1 Z inverse and so on. Suppose the first R coefficients are 0, all right, or rather suppose the leading power of Z inverse is Z to the minus R. Suppose if this were the case, then you can always factor out Z to the minus R. Therefore, P of Z by Q of Z can be written as Z to the minus R P1 of Z by Q1 of Z, by Q of Z rather. And now P of Z by Q of Z, which was the original Z transform, and P1 of Z by Q of Z, where P1 of Z is obtained by factoring out the first non-zero power of Z, Z to the minus R, right. So, these, when you consider the inverse Z transform, differ only by what? By an R sample delay, yeah, time shift. So, differ only by an R sample delay. Therefore, once you find the inverse Z transform of P1 of Z by Q of Z, you can always find the Z transform of P of Z by Q of Z. So, the point that has been made so far is that assuming P of Z by Q of Z to be in this form is not restrictive. And now what we will do is, we will do what you had done for inverse Laplace transform. There you had assumed x of s to be of the form p of s over q of s, and one of the first techniques that was applied was partial fraction expansion. So, we will do the same thing here. It is very similar in principle, but we will point out an important difference. So, the first case we will consider is m strictly less than n. We will also assume simple roots. Therefore, x of z, which is of the form p of z over q of z, the very first thing you need to do when you do partial fraction expansion is factor the denominator. Yes, question. Yeah, simple root means it's each root has power 1. Therefore, for example, if you had 1 by 1 minus a z inverse, then z is equal to a is a pole, but it's a pole of order 1, whereas 1 by 1 minus a z inverse whole squared is a pole at z equal to a of order 2, and that is not designated as simple. Simple means first order roots. So, the very first thing that you do is factor the denominator, and this of course is p of z, and this is written as k going from 1 to cap n a k by 1 minus q k z inverse. By the way, when you assume m to be strictly less than n, this ratio of polynomials is said to be in, you must have encountered this in Laplace. The term that is used when m is strictly less than n, when you are applying partial fractions, what is the term that is used? Proper form. So, this is in proper form, and these are called residues. The AKs are called as the residues, and AK is given by P of z by L going from 1 to cap n 1 minus QL z inverse L not equal to k, and this whole expression is evaluated at z equal to qk. And in this context, you can look up this one. RESIDUEZ. This is the MATLAB command. And the counterpart of this for the Laplace is just residue. And the difference is this. So, if you do, after all, you have a ratio of polynomials b of z over a of z. So, the b vector are the b coefficients that you have to feed to MATLAB. The a vector are the denominator coefficients, and then you have to give this command residue z, and this will assume rational transform of the form b of z over a of z, that is exactly, or rather p of z over q of z, just to be consistent with what I had written earlier. The numerator coefficients as a vector feed it to MATLAB, denominator coefficients as a vector feed it to MATLAB, and MATLAB will give you the residues, and it will also factor the denominator. And in this form, if you give it as a vector to MATLAB, it will assume the polynomial to be precisely of this form. The first coefficient will be P naught, the second coefficient will be P1, which will correspond to z to the minus 1, and so on. Similarly for the denominator. Whereas if you use the command residue, that is applied to the Laplace case, and if you recall in the Laplace case, if the x of s is of the form p of s over q of s, the polynomial is in powers of s rather than s inverse. Okay. So, that is the difference between residue and residue z, the form of the assumed polynomial. In this case, it is powers of z inverse, that is why it makes sense to use this command in this context. And as a simple example, if x of z is of this form, the very first thing that you need to do is to factor the denominator, and this is easily seen to be 1 minus half z inverse times 1 minus z inverse, and is this okay? Yeah, thank you. So, this is z power minus 2. So, this is 1 minus half z inverse plus b by 1 minus z inverse, and all you need to do is multiply x of z by 1 minus half z inverse to cancel this, and then evaluate it at z equal to half. Okay. Right. So, what is a? Okay. So, this is minus 1 by 1 minus half z inverse plus 2 by 1 minus z inverse. And the next step is of course to find the time domain sequence, but to do that you need ROC information from. So, it is very important to realize that at this point you cannot find out what the time domain sequence is unless you are given the ROC, and clearly there are 3 different possibilities here. So, you can have mod z strictly less than half, or you can have the ROC to be between half and 1, and the final possibility is mod z greater than 1, because you have a pole at half, you have a pole at z equal to 1, therefore 3 different regions of convergence are possible. And if this were mod z less than half, then this becomes half power n u of minus n minus 1 plus 2 times u of n. Okay, so you remember both sequences are left sided, all right. So this is already, there is a minus sign here, right. Therefore, the corresponding time domain sequence is this okay? Yeah, because this is left sided, its inverse Z transform is really half to the n u of minus n minus 1. The second one there is a minus n, yeah, right. U of minus n minus 1, sure, thank you. And if it were between half and 1, right, this term must correspond to a right sided sequence. Therefore, this should be minus half to the n u of n, and this stays as it is. Final of course is both of them are right sided. Therefore, this becomes and this is 2 times u to the n. So these are the 3 possibilities. Actually, based on what we have seen so far, this should, are you reminded of something that we have already seen in one of the properties? One of the properties that we had seen, there is a connection between that and what we have just now discussed. Okay, I will tell you what the property is, and then I want you to see whether you are able to catch the connection. The property that this is related to is final value theorem. Yes. Remember the final value theorem, if it had a non-zero value, we saw that must contain what kind of sequence in the inverse Z transform, or rather in the time domain signal. It must contain a component that corresponds to u of n, correct? And that formula is no different from what is happening here. So, in this particular example, you can see it has this kind of term. Therefore, what will be the final value theorem as applied to this given transform, assuming right sided sequence? It will be 2, right. So, basically what you are doing when you multiply by 1 minus Z inverse and compute the limit as Z tends to 1, all you are doing is you are evaluating the residue at that particular pole, that is all. So, this is simple pole. Now, again simple pole assumption, but it is no longer in proper form. So, m is greater than or equal to n. Therefore, x of z, which is of the form p of z over q of z, before proceeding to partial fractions, you have to convert it to proper form, and hence you divide and get quotient and remainder. Therefore, if you do that, this will be k equal to, the quotient will have degree, what will be the upper limit of this sum here? m minus n C r z to the minus r. So, this is what the quotient will be, and then of course, the remainder will be in proper form, and this if you break it up into residues, you apply what we had seen earlier. So, this goes from k going to 1 to cap n a k by 1 minus q k z inverse. And as a simple example, if you had the same denominator as before, and instead now if you had this, you need to first divide and then apply the partial fraction expansion. You have to get the residues, and this if you divide, so this will be 2 plus minus 3 by 2 z inverse plus half z to the minus 2. This of course can be written as 1 minus half z inverse 1 minus z inverse, and this will be minus 1 plus 5 z inverse. This you can check, because if you take multiply this 2 times 1, you will get 2 minus 1, that will give you 1, and 2 times minus 3 by 2 will give you minus 3 z inverse, minus 3 plus 5 z inverse will give you 2 z inverse, and this again has to be so this turns out to be this, and again as before, to proceed from this step to the next in finding the inverse Z transform, you need ROC information. Again, since the denominator is the same, you have 3 possibilities for the ROC: mod Z less than half, between half and 1, and greater than 1. So, this is pretty straightforward here. You had already seen partial fraction expansion in for the Laplace case, and this seems no different, correct? But is there something that you can spot here that is slightly different or has an advantage over what we have been using before? That is okay. So, yeah, actually I should have written that. So, in this case, the inverse Z transform is always k going from 0 to m minus n C r delta of n minus k, the inverse Z transform, independent of the ROC. This term will always be as it is, but that is not what I am after. For example, if you look at this particular example, does that trigger one difference in the way we have been using partial fraction here versus what you have been used to doing partial fractions in the Laplace case? Yes, therefore, that is a good point. Therefore, what is the consequence of that? Here, if you express this in powers of z, the numerator will be z squared, right? So, it is not in proper form, right? Therefore, you have to do something else, or the other shortcut that is normally done is what you have suggested. What you can do is you can take the divide by s, make it proper, and then try to relate the inverse Laplace transform of x of s versus s times x of s. Whereas here, if this were in powers of z, this will not be in proper form. That's all. Whereas in powers of z inverse, this is in proper form, and we are dealing with z inverse here, which is the natural thing to use in this context. And just to illustrate this particular example in MATLAB, so the general form is R, which stands for the residue, P, which stands for the pole, and K stands for the quotient term. And then this is residue Z. The B vector in this particular case is 1, 2, 1, the latest example that we have considered, and the denominator is 1 minus 3 by 2 minus half. All right. So, what you will get here for the k will be the quotient polynomial. You will get all the c coefficients. Remember, we had this, right? The c coefficients is what you will get. So, in this particular case, what do you expect to get as for k? The quotient polynomial is 2. Therefore, you can expect to get 2 here, and then R are the residues, and the residues that you will get are minus 9 and 8, and P are the poles. So, you can get, you will be getting half and 1. So, let us see that here. Did I do this right? There you go. So, R are the residues 8 and minus 9, and look at the order of the poles is, the first pole is 1 and the second pole is half. So, corresponding residues are 8 corresponds to the pole at z equal to 1, minus 9 corresponds to the pole at z equal to half, and the k term corresponds to the quotient. Therefore, MATLAB gives you this very easily. And to go from this step to the time domain sequence, you need the ROC information. And the last case is multiple poles, that is non-simple, and still m strictly less than n. Again, if m were greater than or equal to n, you can always divide, and then quotient you will get similar to what was happening in the previous case. And once you express it in proper form, what the remainder term will have this, and since this is messy, I have it already written down here. So, this is m less than n repeated roots. So, you have the numerator here, all right, and then the denominator is broken down into simple poles and multiple poles terms, all right. So, gamma L is a pole with multiplicity sigma L, that is all. alright. So, as a simple example, if I had 1 minus 2 Z inverse, 1 minus 1 by 5 Z inverse power 2 and 1 plus Z inverse power 4. So, this is gamma 1. Remember, I am using gamma to denote the roots that have multiplicity. So, this will be gamma 1 and this will be the corresponding sigma 1. Similarly, this is actually 1 times Z inverse, therefore, this is gamma 2, which is 1, sigma 2 is 4. Gamma 2 is minus 1, yeah, right. Alright. And the overall degree of the denominator is, you sum up all these things. And now, this is how this can be decomposed as the simple roots as before, no change. For the multiple roots, you need this formula here, alright. And this is how the residues are computed. For the simple roots, no change. For the roots with multiplicity, you have to differentiate as many times as needed. And you need to get the residues up to sigma L. So, what this tells you is, for this particular example, 1 plus Z inverse power 4, you will have 4 residues. For this term, 1 minus 1 over 5 Z inverse power 2, you will have 2 residues. And these are, for the same pole locations, you will get multiple residues. And this is what the formula is. Again, in MATLAB, you can implement this. So, this is 12 minus 22 Z inverse plus 16 Z to the minus 2, and denominator is 1 minus 2 Z inverse power 3, right. So, if you had power 3 for this particular root at Z equal to 2, you will have 3 residues, alright. Again, this can be done in MATLAB very easily. So, all I need to do is I need to feed in the numerator coefficient and the denominator coefficient. And in this particular example, you see the residues are 5, 3 and 4, and this is already in proper form. Therefore, if I apply this to MATLAB, I will get pole which is at 2, I will get 2 with multiplicity 3. So, the vector P will have 3 elements, all 3 elements will be the same, namely they will be 2, because that is where the pole is. And then the residues will be 5, 3 and 4. And because this is already in proper form, K will have a null vector, alright. So, let me so this is R P K residue Z, and then the denominator is 1 minus 2 Z inverse, right. Therefore, that remember you have to give this as a vector, you have to expand the denominator and give the coefficients as vectors, alright. So, this is 1 minus 2 Z inverse whole cubed is 1 minus 2 convolved with itself 3 times. Therefore, you can get the denominator polynomial vector using convolution. So, 1 comma minus 2 convolved with 1 comma minus 2. This of course is, if you remember the formula for a minus b whole cubed, you can get it right away. If you want to do it in MATLAB, the way to do that is like this, alright. And then you need to convolve the answer one more time with 1 minus 2. So, this is the denominator vector. Therefore, residue Z. So, this needs to be of the form R P K and the numerator is 12 minus 22 16. So, 12 minus 22 16 and the denominator vector is 1 minus 6 12 minus 8. Since I already have that vector stored in the variable a and s, I can use that. So, now you see that the k coefficient is null because it is already in proper form. All the poles are at 2. So, you have p with 2 repeated thrice and these are the residues 4, 3 and 5, which is what we saw was happening here, okay, 5, 3 and 4. So, exactly MATLAB gives you this, and again it is good to work a couple of exercises using this formula, but again I do not expect you to remember this. It is not fair to ask multiple roots question on the exam, right, because it is tedious, you can make mistakes. To remember this is difficult, therefore, I will not be asking this. Maybe multiplicity 2 is okay, but beyond that is not this one. And once you have found the residues, you still need to compute the inverse Z transform. And now we are talking about poles with multiplicities, therefore, you need to know the formulas for 1 by 1 minus A Z inverse to the power m. Again, depending upon whether mod Z is greater than mod A or mod Z is less than mod A, the answer will change. So, the region of convergence will dictate what the left hand side will be. If you look at this expansion here, if you look at this, so you have found out the residues and k itself will go from 1 to sigma L. Therefore, you will have for the first term you will have k equal to 1. So, it is of the form 1 by 1 minus A Z inverse power 1, then 1 by 1 minus A Z inverse power 2 and so on. So, you need to know the inverse Z transform of 1 by 1 minus A Z inverse power cap m in general.